Okay, let's go ahead and pick up where we left off last time. And this was our PowerPoint presentation. And I probably skipped a few things in here. Sorry about that. And this is what we called a calorimeter. Yes, it looks like a couple of styrofoam cups with a lid and a thermometer and stirrer kind of like stuck in there. But like I said, for most experiments that we do, this is enough. So this is how you assemble the calorimeter. Last time we talked about the property of heat, right? And this is the property we want to measure here. So remember that the role of the styrofoam is essentially to kind of isolate what's inside the styrofoam cup from what's on the outside. So that essentially everything in the inside of the styrofoam cup remains insulated, and therefore it's kind of like a mini universe. It's kind of like, you know, what happens in Vegas stays in Vegas. That's exactly what this is. So essentially, whatever energy transactions happen inside the calorimeter are going to be a total including what happens in the solution, what happens in the calorimeter itself, and what happens in the reaction. Now, we are interested in what happens with the chemical reaction itself, right? So the total exchange of energy here, because of conservation, right? Since no heat enters or leaves our system, we're going to say that that is going to be zero, all right? Now, for our reaction, if we rearrange this equation, we can see that the heat of the reaction is going to be the negative of the total heat transactions that happen with the solution in which the reaction is happening and the calorimeter. Now, the solution might actually be so dilute that it's almost like it's all just water. But we'll talk about that in the experiment that we're going to be doing later on. Okay, so remember the MCAT formula. So the solution is going to undergo some kind of energy change in the form of heat because there's no expansion here of gases, so there's no work being done. So this will be the mass times the specific heat of the solution times the change in temperature of the solution. For the calorimeter, we're going to have to calibrate the styrofoam cups and find a heat capacity of our calorimeter times the delta T. Now, delta T should be the same for both the calorimeter and the solution because they will rapidly exchange energy and arrive at the same final temperature. Okay, so that's the way it works. Now, remember, because this reaction is happening under constant pressure, you know, essentially the pressure of the air around, right? That is kind of like coming in through these little holes in here. This is not a perfect seal, by the way, so that's going to be the pressure there. Remember that under these conditions, we have a property that we invented, that at constant pressure, the heat exchange that happens here is delta H. In other words, an enthalpy change, which typically you arrive at by calculating the amount of heat that the reaction produced or absorbed divided by the number of moles of reactant that were there, all right? So under these conditions, the heat that we calculate is going to result in a property of state, a function of state. All right, so let's look at this table here. And this shows you a few reactions that you can do here. All right, so for example, the heat or neutralization, that's an acid-base reaction. You can see there that the delta H is minus 56.2. All right. You can look different ones in here. Some of these, for example, the heat of fusion, the heat of vaporization, these are actually physical processes. And by the way, the heat of vaporization of water is a property that we are going to calculate later in the semester, but we're not going to do it by calorimetry. We're going to use a different approach. All right. Okay. So right now, we have these things here, and I showed you those, that previous slide with the setup. Oops, I'm sorry. And you're asking, okay, can we have a practice problem? You are, but the practice problem you're going to have is going to be the next lab. So we're going to have a lab, which is lab 11, called Hess's law. I prefer to call it calorimetry. And in that particular lab, you're going to be doing all these kinds of calculations. that lab is almost ready. So what I'm going to do is I'll kind of finish it up over the spring break, and it'll be ready for you when you come back from spring break. All right. Okay. Now, when we look at this table here, we see like, 5 different things in here. And you can imagine, wow, you know how many reactions there are? There's a ton of them. Now, there's no way to measure the actual absolute value of enthalpy. All we're measuring is delta H. In other words, I have to do an experiment to measure and calculate heat exchange so I can convert that into delta H. Would I have to do that for every reaction that I'm interested in? Well, the answer obviously is no. What we're going to do is we're going to invent a path. We're going to pretend that the reaction happens by deconstructing the reactants and then getting the products assembled from scratch. So we're going to pretend that's the way the reaction happens, and we're going to consider essentially the change between final minus initial as being the products minus the reactants. All right. Now, before we do that, there's a few things we need to do. We need to set some parameters. So for example, we need to make sure that everything has a reference point for all these enthalpy expressions, all right? So we're gonna set up, first of all, a reference point. That's the first thing we're gonna do. And we're gonna call this the standard conditions, all right? Standard conditions. Be careful not to confuse this with STP, standard temperature and pressure for gases. This is a different thing, all right? We're going to try to put products and reactants on the same level field. The standard state is a state of material at a defined set of conditions. So if the material is a pure gas, we're going to set it at 1 atmosphere pressure. If it's a pure solid or liquid, we're going to put it at 1 atmosphere pressure at a specific temperature, usually 25 degrees, and we're going to consider what is the most stable form of that substance under those conditions. There are several things, as we'll see in a few moments. If the substance is in solution, generally an aqueous solution, we are going to set the molarity at 1 molar. Okay, so this is the standard state for different kinds of substances. Now, when we talk about the heat of the process, in other words, the enthalpy change, the delta H, we're going to define what is called a standard enthalpy of formation. Delta H, superscript 0, subscript F, and I don't know if you're familiar with this, but essentially, when we have this little 0 there, we call this, see if I can get my pen to work here. I'm not getting it to work. Okay, it doesn't work. Sorry about that. I was trying to write something in there, but essentially the way we pronounce it is delta H naught, N-A-U-G-H-T, N-A-U-G-H-T. That's the way we say it, delta H naught, or the standard enthalpy of formation. So this is defined as the heat change that results when 1 mole of a compound is formed from its elements at a pressure of 1 atmosphere. Now, here's what's important. If the substance is an element in its most stable form, the enthalpy of formation is going to be 0. So, for example, let's pretend that I'm making oxygen. Oxygen in its most stable form at 1 atmosphere and 25 degrees is a molecule that is diatomic, right? And it's a gas. So if that's the substance we're dealing with, it has a standard enthalpy of formation of 0. However, there is another version of oxygen, O3, which is ozone. That one does not have a 0 delta H of formation. It's 142 kilojoules per mole. So this is why it's going to be important when we write thermochemical equations that we clearly indicate what is the form of the substance we're dealing with. Another example is carbon. The most stable, most common form of carbon is the form that we call graphite. So as long as carbon is monoatomic and in the form of graphite, it has a standard enthalpy of formation of 0. However, in its other form, which is diamond, carbon has an enthalpy of formation of 1.90 kilojoules per mole. Okay? Now, the way this works is I'm going to show you later on a table that you have in your book where you have this kind of information. But these tables look something like this in the next slide here. See the list there? And this one is organized by, the atoms, by the elements. Usually they're organized in some kind of alphabetical order. Several things are important here. Again, notice that for a substance in its stable form, for example, hydrogen, H2, it would have basically a enthalpy of formation of 0. But monoatomic hydrogen would not have the same, right? Also, the physical state is important. Notice over here that water, depending on whether you're talking about vapor or liquid water, has different enthalpies of formation. So when you write the equation, it's very important that you indicate clearly what are the physical states, okay? All right, let's move on right along. And so what is this useful for? Again, what I'm going to do is I'm going to strategize the following. I'm going to take a chemical reaction and I'm going to invent a path for the reaction. I'm going to deconstruct all the reactants back to their component elements, okay? And then I'm going to build the products from scratch using the elements that were obtained from the deconstruction of the reactants. Pretend that you're playing with Lego blocks, all right? You take an assembly of Lego blocks that looks like a truck, and you basically take apart every single Lego block, and you use them to reassemble a building, all right? You have to use all of the Lego blocks that you started with. They all have to be present at the end, but what you have at the end is a different structure. So this is kind of like the path that I'm going to invent. Why can I do that? Well, because remember, enthalpy is a function of state. So when I calculate delta H, all that's important is final minus initial. We don't care how you got from start to finish. All we care of is what is the end line and what is the starting line, all right? Now, before we do that, we're going to have to set up some rules, all right? We're going to have to set up some rules. One of them is, for example, let's say that I'm going to talk about carbon monoxide, CO, all right? We're going to write out what is called the formation reaction for carbon monoxide, all right? The formation reaction. So the elements that make up carbon monoxide are carbon and oxygen. So the first thing we do is we write out the equation, okay? Oh, sorry, I kind of lost track of my things here. Oh, there you go. To make CO. Now, here's the thing. In order for this to be valid, we have to put the elements in their standard forms, all right? In their standard states. So for carbon, there are several forms, but the one that is in the standard state is graphite. And for oxygen, what you have is a diatomic gas. So here is how the equation would look like now. So now I have carbon, notice the specificity there of S for solid and graphite, not diamond, and then oxygen as O2 in the gas form. All right. Now, we had to balance the equation. In the past, all you try to do was make the coefficients match so that they would add up on both sides. But here's the thing with a formation reaction. The formation reaction is designed to yield 1 mole of product. In other words, the coefficient of the product must be 1. So that means that for our reactants, we're going to have to put in whatever coefficient is necessary so that the atoms on both sides will equal without changing the coefficient of the product. That means that, yes, you may have to resort to fractional coefficients. In this case, for example, in order to balance the equation, the O2 reactant has to have a coefficient of 1/2 because we are bent on producing only 1 mole of our product, okay? So that's the rule for the formation reaction. Now, how are we going to use this? Here we go. Let's say that just like we calculated this enthalpy of formation, we're going to calculate the standard enthalpy change for the reaction, delta H naught. This is going to be calculated for all the reactants and products in their standard states. So for example, like we saw before, if I have, for example, a combustion reaction, which involves oxygen, the oxygen has to be in the O2 state gas, right? O2 gas state. We can abbreviate this as heat of reaction, delta H naught, and we can put a subscript there, Rxn for reaction. And everyone understands that's the enthalpy of the reaction or the heat of reaction. And here is the principle that operates in this. Because delta H is a function of state, not of path. In other words, it doesn't depend on the path. That means that you can apply what is called Hess's law. This was derived by, actually it's funny because the name of the guy was Germain Hess, but he was not German, he was Russian actually. So Hess's law is when reactants are converted to products, the change in enthalpy is the same, whether the reaction takes place in one step or in a series of steps. In my own words, what that means is it doesn't matter how you get from reactants to products. All that matters is what are the reactants and what are the products, okay? Let's look at a kind of like a, what do you call it, an emblematic or kind of like symbolic reaction, okay? In this expression of this equation here, the uppercase letters A, B represent the reactants, and the uppercase C and D represent the products, okay? Those are formulas. Pretend they could be elements, they could be molecules, whatever. The small case letters would represent the coefficients in the balanced chemical equation, all right? So the point here is that because enthalpy is a state function, it doesn't matter how you get there, only where you start and where you end. So what we're going to do is create an imaginary path. We're going to invent a path. What we're going to do is we're going to take all of the reactants and we're going to break them down into their component elements in their standard states, all right? And then we're going to take those, like the Lego blocks in my example, and we're going to basically make the products, assemble the products from scratch from their component elements, all right? So let's look at the next slide. And for this, I am going to go to our, I can find it. Okay, I can't seem to be able to find it. Hold on a second, please. I just lost my papers here. Okay, well. Just a moment, please. Okay. Let me hold on a second. I'm gonna pause the recording. Okay, sorry for that brief pause there. I totally lost a paper that I had, so I wanted to show you this. But let's go ahead and go to this piece of paper here, and I'll just do it by hand. Okay, so this is essentially what we're talking about. Let's say that I have a chemical equation, and I'm calling it A times A plus small b times capital B, converting into, small c units of C and D small units of small d units of D. All right. So let's take first of all the reactants. I am going to deconstruct them. In other words, I am going to reverse the process so that instead of forming them, I am actually kind of like breaking them apart into their component elements. So for example, let's say I have A, and I'm going to convert it into elements. So what would be delta H for that process? Well, notice this is essentially the reverse of taking the elements and forming A. So this would be like the negative of the standard enthalpy of formation of compound A. But remember, this is per mole. And I don't have 1 mole here. I have, according to the coefficient, I have A here. So the actual value here would be A moles times minus the delta H of formation of A kilojoules per mole. All right. Let's do the same thing for B now. B would be converted into elements. And the delta H for that would be, well, the minus the delta H of formation of B times small b moles of that guy, right? Okay. Now let's see what we're going to do with the products. We're going to take these elements, all right, and we're going to build the products from scratch. Build from scratch. We're going to use the elements that were provided by the deconstruction of the reactants. Just like the Lego block truck got disassembled, and now we're going to use the same Lego blocks for this. So in other words, I'm going to have some elements, whatever they are, and I'm going to make C, right? But again, this is essentially the formation reaction for C. In other words, delta H for that would be the formation of C, of course, I'm sorry, capital C, times small c, because this is per mole, and this C moles of it. And for D, we do the same thing. Elements forming D. So delta H of that would be whatever the heat of formation, the standard enthalpy of formation of compound, capital D, times D moles. So what would be therefore the total energy change for this reaction? Well, we're going to add all of these, right? We're going to add that and that and that and that. We're going to add them. So what do we get? Okay, so we're going to get essentially minus A times the formation of capital A minus small b times the formation of capital B plus small c times the formation of capital C, and then small d times the formation of compound D. But we don't like having negatives there, right? So how about if we write this in the following form? Let's say this is C, times the enthalpy of formation of that compound plus D times the enthalpy of formation of that compound. And I'm going to enclose those in a bracket, minus, I'm going to put the negative sign out, and then inside my brackets, I would have A times the enthalpy of formation of that compound plus B times the enthalpy of formation of that compound. All right, everybody got that? Now, what is this in the front here? This is essentially the sum or the summation of the enthalpies of formation of all the products. And this over here would be the summation of all the enthalpy of formation of the reactants. And that, my friends, is what we get from Hess's law. All right, that's what it does. I can calculate the energy change for pretty much any reaction as long as I have the data for the enthalpies of formation of every component in there. So let's do a little practice exercise and then we'll take a little break, okay? So let's go to your, I think your next slide here, which is, oops, where are we? Oh, here we go. All right. So here's the plan. What we said is that when we add up all of the components in here, what we get is that this is going to be the summation of the enthalpies of formation of products minus the summation of enthalpies of production of reactants. In here, in this particular case, they put in that, small n and small m. That represents essentially that we actually multiplied times, the stoichiometric coefficients of each one in there. So let's do a little practice problem here. Benzene burns in air, and they give you the formula there, to produce carbon dioxide and liquid water. We've seen this kind of reaction before. How much heat is released per mole of benzene combusted? The standard enthalpy of formation of benzene is 49.04 kilojoules per mole. So this is a very typical type of problem that we would have. And let's go ahead. First of all, let's write down what is the equation for this. Okay, so we're going to give you the equation there. So that's balanced. All right, here are the formulas. Okay. So according to Hess's law, the enthalpy change for this whole reaction would be products minus reactants. So let's see what those would be. So our products are carbon dioxide and water, right? So those are going to be some there. And then there's 12 units of carbon dioxide and 6 of water, minus the reactants, and that would be 2 units of benzene. Dr. Dia, what happened to the oxygen? What about the O2? Well, remember, for an element in its stable state, the enthalpy of formation is 0. So we don't include it in here. Now, where do I find this information? Now, again, in a typical case, you would be provided with that, but I wanted to take a chance to show you where you can get this information. So let me pull out of here for a moment and take us to your textbook. Let me see if I can find it. Okay, here we are. This was your Canvas page. Here is your textbook, your TRO textbook, right? The one that you have access to. And if you scroll here on the left, all the way near the bottom, you're gonna get several appendices. I don't know if you pronounce it appendices or appendices. I'm not an English major, but the one that you're interested in, I'm sorry, the one that is of interest here is Appendix 2. It says useful data. Let's see what that is. Well, they have different things here. The one you're interested in here is this one, B, standard thermodynamic quantities. And when you open that, you're gonna get a table that has all of these substances, and there's several items in there, some of which you will discuss in Chem 1B. But the column that we're interested in is this first column here that has the delta H of formation for every one of those things. All right. They're sort of like in alphabetical order by basically what is the main element in that compound. All right. So you can scroll down here and find the values. Be aware that if you look at different sources, there might be some variations here or there. It's typically not more than, plus or minus 5% or something like that, but you will find those variations, all right? So that is where you're gonna look for data if the problem does not give you the data that you're looking for, okay? So for example, in this case, let's say we wanted to look for carbon dioxide gas, there it is. It says here, minus 39, wow, this is very small, minus 393.5 kilojoules per mole or things like that, all right? Like I said, sometimes when you look at things, they might be a little different. So let's go back here to our PowerPoint, all right? Okay, back to our PowerPoint. All right, here we go. Okay, so we're gonna look up these values and we find out that CO2 gas is, like we said, 3, okay, we're gonna look in the appendices for that. So CO2 is minus 393.5 kilojoules per mole, and there's 12 moles of it. Water, liquid, is minus 285.8. And then the benzene, they gave it to us already at 49.04. But there's 2 units. So we do the math there, plum, 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 and you get to this value here of minus, oops, wow. I just used my highlighter straight on my computer screen. Sorry, I picked the wrong thing here instead of my stylus. Okay, so there we go. I gotta clean that. Gotta get my screen cleaner here. Minus 6,535 kilojoules. But notice that this is for what? For 2 moles of benzene. And the question was, what is the heat released per mole? Notice that it is negative. Most, if not all, combustion reactions are exothermic. So we had to divide that by the number of moles, and we get negative 3,268 kilojoules per mole. And again, how many figures you put in here, we're not going to split hairs with this because, like I said, these values of enthalpies of formation are subject to some variation. So sometimes it's not worth really trying to go into, 1, 2, 3, 4 decimal places at all. We typically keep it to the units, okay? So that is how we solve this kind of problem.